Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 34. In this lecture, we'll discuss pressure. This topic is covered in Chapter 14 of our textbook by Surway and Jewett. We begin this lecture with the most basic definition of pressure. Pressure, denoted by the letter P, is defined as force divided by area. So forces are usually applied to some surface or some area. For example, imagine pushing a box. You might put your hands on that box and apply a force to it. The force that you're applying is being distributed over the area of your hands or the palms of your hands. You can also imagine a box simply sitting on the ground. In that case, there is a normal force being applied to that box. The normal force of the ground on the box is being distributed over the area of the box that is actually in contact with the ground. So the ratio of the applied force to the area over which the force is distributed is referred to as pressure. The object that is exerting the force might be your hands, it might be a box, but it could also be a collection of atoms that are exerting forces on the walls of a container with which they're colliding. So we'll discuss that example in much more detail later. We'll want to measure pressure, and for that we need a standard of measurement or a unit of measurement. The SI unit of pressure is the pascal, named in honor of the French scientist Blaise Pascal. 1 pascal is 1 Newton per square meter. That should make sense. After all, the pressure is defined as force divided by area. Force is measured in newtons, area is measured in square meters, so pressure ought to be measured in newtons per square meter, which is referred to as a pascal. Pressure has many applications. It's a ubiquitous concept, so there are many other units that are also used. In this class, we prefer using the SI unit. However, you should be familiar with these other units as well. For example, chemists often prefer using the atmosphere. 1 atmosphere is equal to 101,325 pascals. 1 atmosphere is a convenient unit because it is equal to the pressure that the Earth's atmosphere applies at sea level. Meteorologists prefer using the bar. 1 bar is exactly equal to 100,000 pascals. So you can think of a bar as a round approximation to the atmosphere. Engineers in the United States often use the pounds per square inch, or the PSI. The PSI is equal to 6,894.8 pascals. If you've ever put air in the tires of your car or a bicycle, you've probably measured the air pressure in PSI. Biologists prefer using millimeters of mercury often, which is written as mmHg. The mm refers to millimeters, and the Hg is the periodic table of elements symbol for mercury. 1 millimeter of mercury is equal to 133.3 pascals. A millimeter of mercury is also known as a torr, named in honor of the Italian scientist Evangelista Torricelli. If you've ever been to a doctor's office and had your blood pressure measured, if you got a number something like 120/80, those numbers refer to your blood pressure in millimeters of mercury. To better understand the concept of pressure, let's do a couple of practice problems. A cubic block of copper with a density of 8,960 and a volume of 0.125 rests on the floor. Calculate the pressure the block exerts on the floor. So we have this heavy block of copper that is at rest on the floor. Gravity is pulling this block down. We refer to that force as the weight of the block. If the floor were not there, then the block would simply fall down. But of course, the floor does not allow the block to fall down. The floor exerts an upward force on the block. We refer to that force as the normal force of the floor on the block. Of course, as the floor exerts a force on the block also exerts an equal but opposite force on the floor. These two forces are an action-reaction pair, and they're related by Newton's third law of motion. So as the floor pushes up on the block pushes down on the floor, with a force that is equal to its weight. That force is distributed over the area of the cube. Not the entire surface area of the cube, but only the area of the bottom face of the cube. So the force is distributed only over that area that is actually in contact with the floor. So to begin with, let's understand the size of the cube a little bit better. We have a cubic block and we know its volume, so we should be able to figure out the length of one side of the cube. One side of the cube should be equal to the cube root of its volume, which ends up being 0.5 meters. We can also calculate the weight of the block. Weight is simply equal to mass times the gravitational acceleration. Notice that the mass of the block is not given to us, but we are given the volume of the block and the density of the copper. So we can say that the mass of this copper block is density times its volume times 9.8. Plugging those numbers in, we find that its weight is 10,976 newtons. We can now calculate pressure. Pressure is force divided by area. The force is, of course, weight, the gravitational force. And the area is the area of one side of this cube, so S squared. We already know what S is, that's 0.5. Plugging in those numbers, we find that the pressure that the block exerts on the floor is equal to 43,904 pascals. Let's do another practice problem with pressure. Atmospheric pressure at sea level is 1 atm, which is equal to 101,325 pascals. Calculate the force due to the atmospheric pressure on 1 square centimeter of your skin. So I assume that you live somewhere on the surface of planet Earth, and above your head is the Earth's atmosphere. Above your head is a column of air that is approximately 100 kilometers in height, and all of that air has a certain amount of weight that is essentially pushing down on you and everything else on the Earth's surface. We'll discuss all of this in more detail a little bit later, but for now, I can tell you that the pressure that all that air exerts is 101,325 pascals. Given that fact, what is the force that is applied to 1 square centimeter of your skin? Now, the centimeter is not an SI unit, so we should probably first convert to meters. I'm using the factor label method here. I recommend using this method. You'll be performing many conversions as we study pressure and thermodynamics. And this is a nice way to perform the conversion. We find that the area of 1 square centimeter is equal to 10 to the minus 4 square meters. Now that we know the area, we can easily calculate the force. Pressure is defined as force divided by area. Rearranging that, we find that the force is pressure, which was given, times the area, which is equal to 10.1 newtons. So all the air above your head is actually exerting a force of about 10 newtons on every square centimeter of your body. Of course, you don't notice this force, you're oblivious to it because you've been living under this force your entire life. In fact, human beings have evolved a strong skeletal system in part to be able to withstand this force. In general, whenever a force is applied to an area, one can discuss pressure. However, in this class, we're primarily interested in the pressure exerted by fluids. So although a solid object, like a block resting on the floor, can exert a force on the floor, we're primarily interested in the pressure of fluids. In physics, when I say a fluid, I really mean gases and liquids. So gases and liquids collectively are referred to as fluids, and all fluids exhibit pressure. We'd like to know where this pressure comes from, and eventually we'd like to be able to precisely quantify this pressure. It turns out this pressure really comes from the collisions between molecules of the fluid and the fluid's container. So whenever you have some gas or some liquid within a container, you can imagine that those molecules or atoms of the fluid are moving around rapidly. Occasionally, those molecules will collide with each other, but more often they will collide with the walls of the container. Every time one of these molecules collides with the wall, it exerts a small amount of force on that wall. Over time, many molecules will collide with the walls, and that force often adds up to a significant force. The ratio of the total force applied to the total area of the container is the pressure of the fluid. We'll have to make this picture much more precise. We'll talk about the exact speed with which the molecules move. We'll talk about the force that each molecule exerts on the walls. But for now, this is the basic picture that you should have in mind. For example, the air in your room consists of a large number of air molecules, primarily oxygen and nitrogen molecules. These molecules are moving around quite rapidly, and they're colliding with the walls of your room. The net force that they apply divided by the total area of the walls of your room gives you the pressure of the air in your room. This simple fact or description of pressure already implies two important properties of pressure. In general, the more particles we have, the more pressure we have. So if we double the number of particles in this box, then we're essentially doubling the number of collisions, and therefore we're essentially doubling the force, and therefore we're essentially doubling the pressure. You should also understand that a higher temperature usually means a higher pressure. We'll make this much more precise later, but for now I'll tell you that when we raise the temperature of a fluid, we're basically forcing the molecules to move more rapidly. So the speed of the molecules increases as their temperature increases. Of course, as the molecules move around more rapidly, their collisions with the walls becomes more violent, more forceful. If each molecule is now exerting a larger force on the walls, the pressure is also going to be greater. We'll develop equations for each one of these concepts eventually, and we'll make it much more precise, but for now you should have this intuitive understanding that more particles at a higher temperature results in a much higher pressure. To better understand the conceptual model I just presented to you, let's do a couple of practice problems. 1 mole of oxygen molecules at a temperature of 300 Kelvin is confined to a box of volume 10 liters. The pressure is measured to be 250 kilopascals. 2 more moles of oxygen gas at the same temperature are then added to the box. What is the new pressure? So first of all, there's probably a lot of new vocabulary here that you need to be familiar with. 1 mole is simply equal to 6.022 times 10 to the 23. So 1 mole is simply a very large number, specifically this number here. When I say I have 1 mole of oxygen molecules, what I mean is that I have this many oxygen molecules, or a little more precisely, I mean that we have 0.6022 septillion oxygen molecules. This is a number that's often used by chemists, and we'll be using it a little bit in this course as well. The temperature of the gas is 300 Kelvin. The Kelvin is the SI unit of temperature. We'll be talking about temperature in future lectures a lot more, but for now, know that the Kelvin is the SI unit which we prefer to use for temperature. The volume of the box is 10 liters. The liter is a unit of volume. It's not the SI unit. The SI unit of volume is the cubic meter. You should know that 1 liter is equal to 10 to the minus 3 cubic meters, or there are 1,000 liters to 1 cubic meter. The pressure of the gas is measured to be 250 kilopascals, or 250,000 pascals. 2 more moles of oxygen gas are added, so we now have a total of 3 moles of gas inside the box. What is the new or final pressure of the gas? We'll eventually develop precise formulas that allow us to calculate things like this, but already you should recognize that if there are 3 times as many molecules inside the box, then roughly speaking, there are going to be 3 times as many collisions with the walls of the box. So each molecule exerts exactly the same force as before, but now there are 3 times as many molecules. So 3 times as many collisions, and therefore 3 times as much force is being exerted on the walls of the container. The size of the box has not changed, so area remains constant, but the force is tripled, and therefore pressure must be tripled as well. Recall that pressure is force divided by area, and so the new pressure, or the final pressure of the gas, should be 750 kilopascals, exactly 3 times the initial pressure. Here's a related problem. 1 mole of oxygen molecules at a temperature of 300 Kelvin is confined to a box of volume 10 liters. The pressure is measured to be 250 kilopascals, exactly as before. The gas is then moved to a box of volume 20 liters. Does the pressure increase or decrease? So we're simply moving the gas to a new box with a larger volume. The number of molecules remains the same, so we should think that there are just as many collisions as before, but a larger box has a larger surface area. So the force of those collisions is now distributed over a larger area. Remember that pressure is equal to force divided by area. If the area increases, then the pressure decreases. Later on, we will find that when the volume doubles, the pressure basically becomes half as large, although there are some caveats, and to be careful about it, we won't do any numerical calculations. For now, we'll discuss the numerical calculations a little bit later. So let's end this lecture with one final practice problem. Each of the 4 tires of an automobile has an area of 24 square centimeters that is in contact with the ground. Each tire is inflated to a gauge pressure of 200 kilopascals. Calculate the mass of the automobile. So once again, there's probably some new vocabulary here. Notice that we're talking about gauge pressure here. Gauge pressure is a little bit different than the pressure or the absolute pressure that we've been talking about so far. To be a little more precise, gauge pressure is equal to pressure, that's the pressure we've been talking about, sometimes referred to as absolute pressure, minus the ambient pressure. The ambient pressure basically refers to the pressure in the environment or surrounding the object of interest. The ambient pressure is usually assumed to be atmospheric pressure, or 1 atm, although if you live at extremely high elevations, your ambient pressure might be a little bit less than 1 atm. So when we talk about gauge pressure, we're really talking about the relative pressure. We're talking about the pressure above or below whatever the ambient pressure is. If we were to actually measure the absolute pressure inside the tires, we would find that the pressure of the air inside the tires is really equal to the gauge pressure, which is 200 kilopascals, plus the ambient pressure, which, if we assume that's about 1 atmosphere, ends up being approximately 100 kilopascals. So the actual pressure, or the absolute pressure inside the tires, is approximately 300 kilopascals. However, for this problem, we don't really care about the absolute pressure. What we care about is the gauge pressure. The reason is that we're trying to find the mass of the car, and the mass of the car is related to the weight of the car. The weight of the car, of course, is the force of gravity. That's the force that we actually care about. We don't really care about the force that the surrounding air, the atmosphere, is exerting on the car. So we want to really ignore this 100 kilopascals here and concentrate on the 200 kilopascals, or the gauge pressure. Now, as a result of the weight of the car, the tires are no longer perfectly circular. The bottoms of the tires are flattened a little bit. The area for each tire that is actually in contact with the ground is 24 square centimeters. I'm not talking about the surface area of the tires here. I'm talking about the bottom area of each tire. So if this car, for example, were parked on sand, the impression that each tire would leave on the sand would have an area of 24 square centimeters. Given this information, can we calculate the mass of the automobile? Well, the gauge pressure is 200 kilopascals, or 2 times 10 to the 5th pascals. The area is 24 square centimeters. We should convert that to meters. We find that the area for each tire is 0.024 square centimeters. Again, that's the area over which the force of weight is being distributed. And now we can calculate the force. Let's start with one tire. We know pressure is force divided by area. So force is going to be area, which we have found here, times the gauge pressure, which is given here. We find that the force that one tire supports is 4,800 newtons. Of course, the car has 4 tires, so the weight of the car must be 4 times this number. We find that the car's weight is 19,200 newtons. The question asks for the mass of the car. We know that weight is equal to mg. Rearranging that formula, we find that the mass of the car should be 1,959 kilograms. And that is the end of this lecture. Thank you for your attention.